have two types of solutions here. I will discuss about that. First part, we'll go to what happens if we calculate the beta directly, because frequency is given. Maybe we think that we can directly apply that part, right? So let's go to that and we'll try to solve and see what happens. So what's the beta you get when you solve directly? Because f is given, frequency is equal to 1 kilohertz, correct? Right. So you can find C, right? And then directly you can find the beta. So what's the lambda? Yes, so C by F, that is 3 into 10 to the 8 divided by, this is 1 into 10 to the 3, 3 into 10 to the 5 meters. Okay. Yes. Okay, that's fine. Now, what's the beta you get? Beta is equal to 2 pi by lambda. All right. So that is 2 pi divided by 3 into 10 to the 5 minus 5. Okay. Right. Okay. So once we know the beta, we can find the velocity, right? Anyway, we'll come to the velocity part later. Okay. Right. That's one method, but right, I'll tell you about the another method, which is now we see in this question they're saying about the why we cannot apply the 1 kilohertz. I'm trying to answer that question, right? So it is the question here, these values are obtained at 1 kilohertz. Okay, so it is not that you are sending 1 kilohertz always. Frequency will vary now, right? So which means, right, the 1 kilohertz, right, was used when you try to calculate the ZSC and ZOC, right? So for calculating this ZSC, ZOC, yes, you use 1 kilohertz. At 1 kilohertz, this is what is obtained. Okay, right now. So in the question, in order to find the phase velocity, right, you need to calculate the beta value, right, which is corresponding to that line. In the sense, what should be the gamma value of that line? I need to calculate. Once you calculate that, then you will be able to do this. That's why, right, we don't go with the 2 pi by that method directly. Okay, right. So now, anyway, the calculation of beta will happen like this if it is a fixed 1 kilohertz, right? But in this question, ZSC and ZOC were found at 1 kilohertz. That's all. Okay, so that's the difference. All right. Okay, so let me start from here. This is the point where we had stopped, right? We'll continue from there. Okay, we'll apply the another method, right? And we'll try to find out. Okay, so let me write down that once again. So this is what is known now. So that is gamma L was equal to tan H inverse of 0.297 minus 29 degrees. Okay, right. So what we do, we take the tan to the other side. So tan hyperbolic. Okay, so you're saying that this value what we entered is wrong. Okay. Okay, yeah. Okay, yeah. Please come back. I'll correct that. So which I should change. This should be inverse of this, right? Whatever I entered, I'll just take a bracket and I write inverse. Is it okay? Okay, now you tell me the exact value what you get. I'll update. Okay, 3.35 at an angle 29. Okay, so that is 29 degrees. All right, so that means I don't need this anymore. So anyway, this is so 3.35 at an angle 29, right? So tan h of gamma L is equal to 3 point, I'll correct even here, 3.35 at an angle plus 29 degrees. Okay. Uh, 3.35 at an angle 29. Okay, fine. Now I need a gamma L. So tan h inverse of a complex number is, anyway, we don't have an option, right? That's why we have to substitute what is the tan h of gamma L function. So tan h of gamma L is nothing but it's a uh, we are doing the yeah. So minus e to the power gamma L divided by e to the gamma L plus e to the power minus gamma L. So right hand side, I still have the same thing. Okay, so that is 3 point. Yeah, that should be fine. That's what I need. Okay, 3.1.624. Okay, now okay, what we can do here for simplification. Okay, there is one rule here in mathematics that's what we are going to apply. Let me assume that I have x by y is equal to, say, L divided by m. Okay, all right. I repeat. So you can see here, right? There is a rule in mathematics for fractions, right? Whenever we have a fractions, we can do this. So the x plus y by x minus y will be equal to L plus m by, right, L minus m. So that's the rule, right? So this is what you can apply, right? We try to apply this so that I try to get only gamma L on one side, right? I can see that if I add this and this, right, I get e to the power 2 times e to the power gamma, correct? So e to the minus gamma L I can try to cancel. Similarly, I need to divide something in the denominator so that, right, I'm able to cancel it out. So if I do the denominator minus numerator, what happens? So this is going to get cancelled. This will cancel. This gets added up. Let's do that. Ah, that's what. So they'll add. So the minus this will be 2 times, correct? Right. Okay. So let's try to do that. So that means the first term numerator will be denominator plus numerator. Okay, that's what I'm writing in the in the numerator part. So I'm doing y plus x. Denominator is y, numerator is x for me. Okay, so I'm doing y plus x. Y plus x in the sense e to the gamma L plus e to the gamma L plus c to the minus gamma L plus this plus this. So you see that the minus e to the power minus gamma L and plus e to the power minus gamma L will cancel, right? So I'm doing y plus x, okay? Y plus x and y minus x. It's interchangeably, you can use it as and when, okay? So I'll do that. So that means what happens? Numerator becomes 2 times e to the power gamma L, right? I'm adding these two now. Other two terms will cancel. Hmm. Yes. So 2 e to the power minus gamma L is equal to, let's do that. So denominator here it is 1, right? So this is 1 plus 2.929 plus j 1.624 whole divided by, this is 1 minus 2.929 minus j 1.624, correct? So as you told, this will get cancelled. So this is e to the power 2 gamma L. Yes, can you simplify the right hand side? Yeah, okay. So real terms you try to simplify. So this is a 3.929 plus J1 point. Yeah, we'll come to that. We'll come to that. No, no, we have a solution. Okay, for that we have a solution. Right. So just give me a simplified answer over here. Right. Should be minus 1 point. Uh, okay, the final answer, right? Okay, okay, fine, fine. I'm writing this. 1624. Yeah. So tell me, what's that? 0.51. Now, as it is, I cannot apply this to the anti-log or whatever. So convert this into r angle theta. Okay, so e to the power 2 gamma L 162.360. So I'll write it in the proper format, that is 1.68 e to the power j 162.363. Okay, so now 2 gamma L is equal to anti-log, right? So e to the power, cancel that by using a log on both sides. So this is 1.68 e to the power j 162 point. But actually you see, now the problem is I cannot write in degrees. I have to write in radians. Okay, so when you write, okay, give me the one, that number, 162 point something, equivalent in the radian. Yes, yes, sure. Take your time. 2.83, correct? Okay. So this is a term. So I can split it as ln of 1.68 plus j times 2.83, correct? Because e and ln will cancel. Now this is easier, right? Uh, so first we'll find what is 2 gamma. Hmm. So this is 0.51, okay? Right, so j 2.83. Now I know the 2L, right? 2L, L is given, I guess, right? 10 kilometers. Not given. Let me just check once. Okay, so 10 kilometers. So that means, right, I can apply the formula, the value of L in the formula. So this is the same number divided by 20 kilo, correct? Because 2 into 10. So 20 into 10 to the 3. Yes, 20 into 10 to the 3. Actually, you have an option, like if you want to keep everything as a standard per kilometer, right? No issues, right? You can divide by 20. Only just divide that by 20. That's if sufficient. Okay, so the gamma comes per kilometer. That's all. Yes, yes, yes. That's also fine. Hmm. Huh. Okay. Minus 4. Okay. Right. So we know that we got a beta, right? So beta is equal to 1.10 to the power minus 4. All right. So you got a beta now. So can use this beta to calculate a VP. phase velocity is omega by this beta. So, all right, 2 pi. Now you can apply that given frequency. Okay. Yes, 1 into 10 to the 3 divided by this beta. 1.415 into 10 to the minus. Sure, sure. 10 to the 6 meters per second. So if at all you represented beta in kilometers, right? So then I will be getting kilometers per meter, that kilometers per second. That's all. Okay, right? So that's the solution. Do you have any other doubt with whatever we discussed so far? Okay, let's proceed further. We'll directly move on to the concept called the stub matching. Now, we have seen that the transmission line can be used as for matching, right? In the sense, I can get any device out of, I can form any device out of by using the different lengths and different orientations of the lines, such as lambda by 4, lambda by 2, and I can use a short circuit, open circuit, etc. I can use them to get a specific type of circuits if required, right? So that means I can actually, right, let me assume that I have this is just an example, right? Let me assume that I have a complex load, right? Normally the load will be something, load will not be real, right? Sometimes because of the complexity, right, it may look like this. It's a complex, some ZL is there, right? But we know that we have to have a Z naught, which is something like a real value for lossless case. Correct? I don't want have to have any loss, in the sense whatever is sent should be absorbed by this. But if the ZL is complex, it will not absorb, it will reflect. Okay, right. So you see that what is the requirement for the power, for the supply, right? This ZL should look like a real load, correct? So ZL should look like real means you should cancel the effects of this inductance, isn't it? So what we do here, I know that using a transmission line here, if I connect in parallel, maybe short circuit or open circuit, right? I can, so corresponding to this inductance, let me say that I have a JX that is coming into picture. The because the ZL is equal to some resistance plus JX, correct? Okay, so what we do now, by using a line, right, by using some maybe if it is an inductor, definitely I can go for a short circuit. I can try to create, right, a minus JX here, correct? This, when you look into this side, it should look like minus JX4. You use a short circuit, open circuit, doesn't matter, right? It depends on what various options we have. We'll see that later. Okay, so if you look at this side, it looks like R plus JX. Look at this side, it looks like minus JX. So, right, I can just add them up together so that you can see simply a R value. Correct? Are you okay with that? So that means when you look into this, it looks like a resistance value R. Maybe if at all it is matched to Z naught, absolutely fine. Correct. So Z naught and Z naught are matching. So the whole, right, transmission line, when you look from the input side, it simply looks like a real value. That this is the ultimate goal of a matching. Okay. Right. So now what are the parameters I need to calculate here? First thing is that where you are connecting, from at what distance you are supposed to connect this particular line. So we call it as L. That is the length on the original main transmission line where I'm going to place. This is called as a stub. Okay. This is a stub. Where you are placing that, right? It's called as the location of the stub, measured from the load side. All right. First thing is that. The second one is that what should be the length of the stub that you connect, because depending on the length of the stub, the this jx will vary, right? The actually impedance will vary according to that. More length, more resistance; lesser length, lesser. So exactly to match the whatever uh, complex or the whatever impedance we have, in order to match that, I should have a specific length that needs to be calculated, right? So that is L dash. Okay, so two parameters we need to find. Is it okay? So what are the two things we will count? First one is the position of the stub from the load, right? That is L. And at that position, I'm going to put a stub, right, of length L dash. So these are the two things we need to calculate for matching. Is it okay? Right. So this is a stub matching. We have two cases here, two possibilities. One is a single stub matching, one more is a double stub matching. Right. So right, two things are there, right? So I'll directly move on to the first type, that is a single stub matching. Now we'll write a neat circuit. Okay, so here, okay, let me draw. Let me assume that we are going to insert the stub at this position. Okay, so let's assume that this is the stub which we are talking about, and I'll show this as a short circuit. All right, so this is, I show this as a resistor, but this will be a complex value, right? So I'll write this is the ZL, which is not equal to Z0. If at all it matches, then we don't have any problem, right? So it's not matching. So because of that, right, now we have to use stub for matching part. So first thing is that I want to measure this distance. Okay, so that distance I denote it as L, the length of the stub, and sorry, the position of the stub from the load. That's the first thing. Okay, and the second parameter which I want to measure is this distance from here to here. So that is what I want to calculate. Let's denote that as L dash. Okay, so and we, most of the time the practical case is using a short circuited stub. Okay, you place a short circuited stub over there. So as you move this direction, it is, you move towards the generator power supply. So this is the transmission line which we are talking about. Now our intention is to calculate the L and L dash. All right. Okay. So now, so again, almost 99% of the time where you apply this circuit, you apply this for a microwave frequency, right? Recall the initial classes where we discussed about various types of lines. When you move to the microwave frequency, very high frequency, right? The Z becomes simply R. Z naught becomes R naught. Do you remember that? Somewhere, I'll try to show you that. I think I have written that. At high frequencies, the R becomes equal to 0. Let me see where I have written that. Do you remember something? I'll quickly try to find out where I have written. Yeah, here. Yes. So at microwave frequencies, the omega L is very large, right? Omega C is also very large. So R and G will not come into picture, right? So you see the Z naught equation is simply omega L by omega C. Omega cancels. Its root by LC, we called it as R, right? It's a resistance which is not complex. That's why you can call it as a simple R naught, okay? Right. So this is what we had discussed. Now we are going to that part because matching the using the stubs at other frequencies uses a different concept, right? So as of now, our intention is simply to learn a stub matching concept. Again, we want to keep it as simple as possible. Okay. So all the textbooks of the B level will assume that you are using a microwave frequency signals only. You are not going for any low frequency signal, right? Okay. So at microwave frequencies, the Z naught will be equal to R naught, which is a pure resistance. Okay. Right. Now, let us assume that, right, we want to move at from the load end a distance that is equal to L. All right. So whenever we move by a distance of L, right, we will be assured that when you look into the transmission line over there, you will find out some impedance, okay? Possibly R1 plus JX1, something like that. You will see that it's a complex value. And that is not equal to our real value of the Z naught, right? First thing is that Z naught is real because of the microwave frequency. Second thing, I move a distance L from the load, I will see that there is a complex load. Correct? Okay. Now I'll come to the, I'll write something so that this becomes easy for you. The same thing will even apply on the Smith chart later to solve the problems. Okay. Right. Okay. So just remember these concepts, right? What we are writing. Okay. The first thing is at, right, microwave frequencies. At microwave frequencies, right, just recall the Z naught becomes equal to R naught. That is, right, purely resistive. It's a resistive component. No inductance, no capacitance. Okay, that's the first thing. Right. The second concept is that we try to move a distance L from the load. We move a distance L from the load such that now I have a requirement. Why I move a distance L? Because of one reason. Now you see, at this point, right, in the sense, the load value, let me assume that it is R dash plus some J X dash. Let me assume, right? When you measure the load value, it looks like r dash plus jx dash. Okay, but when you move a distance, on every point on my line I have different impedances, right? You measure here, you find a different value. Okay, you find here, you get a different value. Now I measure here, I should get a different value. Okay, but I will move a distance L. It is unknown, it is not known so far. Okay, but I'll try to make sure that I will move sufficient large amount L where I will match the real component to the real component of the load. In the sense, what I already know something. What I know that this Z naught is equal to R naught, correct? Some resistance value. Now I will move L such a way that when I look into the circuit at that point L, correct? This, right? I will see that this is some R naught plus Jx, correct? Because anyway, Z continuously changes. Let me give an example to make you understand. Let me assume that this Z naught is equal to R naught, which simply 10 ohms. Okay. Now let me assume that on the load end, right, I have a value which is equal to say 15 plus J12. Possible? Okay, but I will try to move a distance L such a way that the real part matches to this. In the sense, I'll get 10 plus J16 maybe. Okay, I have to move by a distance, certain distance L, such a way that the real parts of my impedance that I see into the load is matching with the Z0. Why do you do that? Because short circuited stub will be minus J16, so that you see 16 cancels, your remaining 10 will match to this 10. That's the only reason. Okay, I am not able to match the 10 with the 15, right? 15 is there, right? On the that we cannot match, because whatever you do, right, on the right hand side I have 15 which is the load and 10 which is the Z0, correct? It is not, you are not going to match that at any case, right? So you have to do this, right? Same step you recall, you will be able to recall when we solve the stub matching problem on the Smith chart. I have to move it first, I have to move a distance L, right, somewhere, so that the real value of the load looks like the characteristic impedance. Real value only. You don't have to match the complex part. Complex part we will try to cancel that by using the stub. Is it okay? That part is fine, right? Okay, I'll erase what is not required. So all these are not required. This is just okay, fine. No, so now I'll write that as a point. Okay. So that means, so that's we were discussing about the second point, or this is the step to solve the stub problem. Okay, so we move a distance L from the load. Okay, such that uh, we obtain an impedance, right, that is equal to the same R naught plus some J times X, all right, on the line. So till here it's fine. Is it okay? I understood, okay, this should be the length. How to calculate the length? Mathematically, we have a formula, right? We'll derive the formula now. And but again, if the question is asked by just calculating the length and the length of the stub, it becomes very simple because you have a formula, simply substitute, you get. But what actually the problem comes is use a Smith chart to do that. Okay, so that's the actual problem which we'll solve. All right. Okay, so now I had something like this, right? Resistance. I moved a distance such a way that whatever Z naught equal to real value I had, now here I get the R naught plus some Jx. Okay, at this particular point, I know that where I should put the stub now. So the next question is, what should be the length of this stub? Okay, so what length? That is denoted by L dash. Okay, so the next point is to find out that L dash, right? So the length L dash of the stub required to be found. Okay, so find L dash, that is the length of the stub to be attached. To be attached to match the load. So that whatever is the uh, impedance we obtain, right, that will match the required load. Okay, so this is the whole concept, right? So even the same thing we can apply while we derive. Okay, right, now let us try to find out. Let's start with the equation of the Z in. So right, so we know that, start with the equation of Z in, input impedance, that is equal to Z naught, right, times ZL plus Z naught tan hyperbolic of gamma L whole divided by, this is Z naught plus ZL tan H gamma L. Okay, so this equation we know, this is how we calculate the Z in of that. Now, normally, again, we will see that this concept even in the on the Smith chart. If you use impedance, you see what is our orientation of the stub and the line. Are they series or they are parallel? Look at this direction. You look into the load and tell me whether you are connecting them in parallel or in series. The two things. Parallel, right? So whenever you have consider that you are connecting two resistances in parallel. Okay. The equivalent resistance is, you cannot calculate simply by adding something, right? You need to do a like R1 R2 by R1 plus R, right? So compared to the simple addition, this is a complex calculation, correct? Yes, definitely we can do. We have calculators, we can do that, but right. But this process is slightly difficult, right? R1 into R2 by R1 plus R. Okay. Whereas if you use admittance, right, what happens to the admittance when you have two resistors in parallel? Admittance, what is the total admittance? So if you see, in the sense, if I want to calculate the Z of this input, right, look at this. So I have Z1 and Z2, let's assume. The Z will be calculated as, yeah, correct. Okay, I will update that. So Z is equal to Z1, Z2 by Z1 plus Z2. Okay, but I don't want Z now. Okay, but instead of, yeah, what you told is right. In the sense, I have to, if in terms of Z, if you want to calculate, it is Z1 plus Z2 by Z1 Z. But I don't want that. Let me assume that I have a Y1 here and I have a Y2 here. What is Y in terms of Y1 plus Y2? No, no, no. No, 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 no. Okay, I'll come back. I'll go to the basics once again, right? So how do you calculate the total Z? Total Z is 1 by Z is equal to 1 by Z1 plus 1 by Z2, isn't it? Now, what is 1 by Z? 1 by Z is Y, right? You see, if you try to represent the parallel circuit in terms of admittance, it becomes simple addition. Yeah. So like resistors are in series, admittance becomes series calculation, right? So admittance calculation becomes addition if you have parallel connection of resistors. Okay. So that means what? Anyway, I erase this. This is not needed, right? So you are able to recall. Okay, I'll just erase this. So my point is, I don't want to write the equation for Z in what I have written here. I don't want to maintain this equation because the calculation in terms of resistance is going to be very difficult, very tedious if I retain this Z in my equations. Okay. So what I do, I simply convert them into the admittance. Okay. So Why do we do that? You understood now, right? Converting to the admittance, right? So what happens? The Z in is Y in. Z naught becomes Y naught. All right. So ZL becomes YL plus, right? This is a Y naught into tan H gamma L whole divided by, this is Y naught plus YL tan H gamma L. All right. Absolutely fine. No problem with this. Now again, I can make a change, right? I am assuming that, right, it is a high frequency line, right? So at microwave frequency, what happens to the above line? Can you suggest what is the change that I'm supposed to do at a high frequency? Hmm. What is the change that I can do in the above equation, right? Anyway, y has nothing to do. Don't worry about y. So you need to suggest about the gamma. Why not yl? Y will not change. So what happens to gamma is my question actually. What happens to gamma? Hmm. So gamma is alpha plus j beta. So yes, so in that something will happen. We already have studied. Beta will be there, alpha will not be there, right? Alpha is smaller. So that means, yes, yes, yes. So that means you see that the alpha equal to 0. That implies I can simply write gamma is equal to j times beta. Okay. That's the first thing. Anyway, I'll update my equation first, then we'll make another modification. Right? That's what we are going to see on the Smith chart. So according to the Smith chart requirement, we'll make a small changes later. Okay, so this becomes, this makes it y in is equal to, I'll write y naught into, this is y naught into, we have yl plus y naught tan h of j beta l all divided by tan h of j beta l all divided by denominator should be y naught plus yl tan h j beta l. So use a property from the property of a tan hyperbolic. Tan hyperbolic of j theta is equal to j tan theta, correct? So let's do that. So this is y naught into yl plus, I can write maybe, so j times y naught into tan beta l. Is it okay? I'm trying to write in tan hyperbolic of j theta is j tan theta all divided by denominator is y naught plus j yl tan beta l. Is it fine? Okay. Next is that this is an important step that is a most common step for our Smith chart problem. That is called as a normalization. I think I brought the term called normalization, right? Normalization in the sense you divide the whole equation by the characteristic value, right? If it is impedance, you divide everything by uh, maybe Z naught. Otherwise, you divide everything by Y naught. In this case, Y naught, because Y naught is my term, right? So I'll move. Okay, so just remember whatever I have written so far are the capital letters. Okay, so that's the convention I follow. Normalized will be small letters. So this is Y in. Okay, Y in is equal to, see, capital Y in divided by capital Y naught. So on this side I have Y in. So I move this to this side. So I get on the left hand side normalized. Okay, so this small letter y, what I write is a normalized. Okay, so I'll write here. So normalizing. Right, that is equal to, right, on the right hand side what happens, anyway y naught is not there, I need to divide both the numerator and denominator by y naught. Are you okay? So yl, I have yl by y naught happens, I'll write it as small yl. Okay, plus j times, see the y naught is cancelled, right? So on the, in the first term, so this is plus j times, there is no y naught, so it's simply tan beta l whole divided by denominator y naught is cancelled, so this is 1 plus j yl by y naught is small y. Are you okay? Into tan beta l. So this is the normalized representation. Are you fine? This is what we use, right? Even in the Smith chart problems, right? We need to convert everything into the normalized case first. So beta L is that. Now I need to simplify this further. So what I do, I write, uh, I will, okay, what is the method you use to simplify such terms when you have a complex term in the denominator? Direct mathematics, nothing to deal with that. What do you call that? Anyway, I'll write that. You try to get a name for that. Plus j times tan beta L tan beta L divided by, this is 1 plus j y L tan beta L, multiply and divided by the conjugate of the denominator, isn't it? 1 minus, you call it as a rationalization, right? This is 1 minus j times, we have yl tan beta L whole divided by, this is 1 minus j yl tan beta L. Okay, so what happens to the numerator now? Numerator becomes, so I have yl as it is. What do I get? How do, okay, let us try to multiply the terms, right? So this is yl plus j. Okay, let's multiply. Let's multiply and see. Directly I can say one step here, so let's do that. So yl into 1 is that, okay, yl as it is, yl into minus jyl, so that gives you minus j times yl square tan beta l, isn't it? That's the first term. Then plus j tan beta l, then plus into minus is minus, j square is minus 1, so plus, right, yl tan square of beta l. Are you okay with the numerator part? Tan square of beta l. This whole thing divided by denominator becomes, right, 1, uh, it's a square minus b square, right? A square is 1 into 1 square minus b square. So j into j is j square, so it becomes a plus yl tan, sorry, yl square I guess, right? So yl square tan square of beta l. Is it fine? Okay, now what I do, I got a y here, right? It is at a distance L from the load, correct? This Z in is, if you put the L as the complete length of the line, I get the Y in. isn't it? I'll quickly go back to the diagram just to make things clear, right? I started with the equation of Z in, assuming that I know the complete length of the line. But if I make sure that, right, I will put this in the equation of Z in, that L, right, that is required to convert the real part as some R naught plus JXL, right? Then that's the length I want, correct? I want to find out that whatever length I'm supposed to calculate, that L makes the, right, the value of, in this case, we are dealing with the Y in, okay? This Y in should be equal to the actual Y in of my line. That's all. Okay, right. So let's do that. Okay, so this is my equation. So in this case, I am supposed to look at the real part only. I don't want a complex part. The equation is complex, but I want only I want to look at the real part. Okay, so what I do, I try to separate the real and the imaginary term, right? The real term is going to be, right, the real term. I have a YL. Uh, what are the terms giving me YL? Okay, the first and the last term in the numerator are real, correct? So YL is common. So YL into 1 plus tan square beta L is the real term, divided by 1 plus YL square tan square beta L. Okay, that's the real term. Then let me separate the complex term here. Okay, so that is plus J into, take the J out, 1 minus YL square into tan beta L whole divided by the denominator. That is 1 plus YL square tan square beta L. Are you okay with this? This is the Y. Okay, so I want to compare this Y in as some G part conductance, some G dash plus J times B dash, susceptance. Okay, B dash is a susceptance. Fine. Now, let me come back to the point, right? I just now I discussed, but I want to tell this once again because right now what I'm looking at is related to this equation. In this equation, we told, I'll quickly draw the previous case. So we had something like this where I have some R naught here. There is some value, some R dash plus X, sorry, J times X dash, right, as a impedance. I moved by a distance L such a way that here I am going to see R naught plus some other J times X value. Okay, that is what is my point, right? I moved by a distance L, but at this point, I am not looking at the R term, I am looking at the Y term, correct? So Y term means this G dash, whatever we are looking at a G dash, I should deal with the G dash part, right? I'm going to look, I'm going to bring bring the uh, bring up an equation in terms of this Y term, not in terms of resistance. In terms of resistance, R naught and R naught should match. Real term R naught should match with the real part of the R, correct? That's what is the point. But since I am looking at the Y term, right? What is the point here? The okay, I'll write a point here. So anyway, this diagram is not needed when you write any answer, right? When you answer a question, right? But this point is required, right? If no reflection from the load, correct? No reflection is expected from the load. We normally say that the Y R naught and R in should be same, correct? Otherwise, now I don't write in terms of R naught, I will write in terms of Y, correct? Because right now my calculation is happening with respect to this. So that is the Y in should be equal to Y naught in terms of Y. Okay, but I don't have capital Y in and capital Y naught with me. What I have small y, correct? Small y in should be equal to capital Y in by capital Y naught, that is equal to 1. Are you okay? Because I'm simply moving this to down. Because of no reflection condition, this is the way, right? Whatever Y in you calculated, right, that value should be equal to 1. Now you see, anyway, I'm going to cancel the JB dash part in the equation. Just now we wrote the equation for the JB dash, correct? So in this Y in, G dash plus JB dash is what we have, out of which anyway I'm going to cancel the JB dash part later by using the length of a stub, right? So right now my intention is to make this G dash equal to 1. Are you okay? So that means whatever G dash equation I just have derived, that I should be equal to, I should be I'm equating that to 1. Okay. So this implies the G dash should be equal to 1. So write that condition. So just look at this. YL into 1 plus tan square beta L by 1 plus YL square tan square beta L. This part I am equating to 1. Okay. Let's do that. That means, so I'll write YL into 1 plus tan square beta L all divided by, this is 1 plus YL square tan square beta L should be equal to 1. Cross multiply. That means YL, I expand and write, okay, YL plus YL tan square beta L should be equal to, this is 1 plus YL square tan square beta L. I multiply. Right? The tan terms I bring together, right? So that means YL. On the other side, I have a minus YL. So it's, I'm taking the right hand side to the left side. Okay. So there is YL and YL square inside the bracket. The tan square term is common. Correct? Beta L is equal to 1 as it is. YL goes to other side as minus YL. Okay. So here what happens? Here I can see that I can take YL once again outside. YL 1 minus YL tan square beta L is equal to 1 minus YL. So you see this 1 minus YL cancels. Okay, so that means tan square beta L is equal to 1 by YL, right? So that means, let's move further. What is tan beta L? 1 by root YL. Is it okay? 1 by root YL is nothing but square root of YL is capital YL by Y naught. So this is capital YL by Y naught. Are you okay? That can actually be written in terms of, because we don't know Y. When the equations are given, I am supposed to use the Z only. But calculation purpose, we converted into the Y. Now I'll write in terms of the Z part. So that is ZL by Z naught. Is it okay? So tan beta L is this term. So what you want to calculate a, okay, let me go for beta L. So beta L is equal to tan inverse of root of ZL by Z naught. Are you okay? That means L is equal to, take a beta to other side. So 1 by beta times tan inverse of root of ZL by Z naught. Okay, so anyway, I have the ultimate equation. Beta is 2 pi by lambda. So this is lambda by 2 pi times tan inverse of square root of ZL by Z naught is the equation that we are going to use to find the position of the stub on the transmission line.